Welcome to G Fun Facts Online. Today, we're journeying deep beneath the Atlantic Ocean to a time when dinosaurs roamed the Earth and the continents were being torn apart. An incredible discovery has been made there, rewriting the very history of our planet. Scientists have unearthed gigantic 117-million-year-old structures buried deep beneath the seabed. These are not waves of water, but colossal ripples of sediment, some a kilometer long and hundreds of meters high. This groundbreaking find, located about 400 kilometers off the coast of West Africa, is forcing geologists to rethink the timeline of the Atlantic Ocean's formation and its dramatic impact on the global climate. These silent, buried giants of the deep are now speaking to us, revealing a story of continental breakup, ocean birth, and climate transformation that unfolded over millions of years. So what exactly are these colossal underwater structures? Deep beneath the waves, in a realm of perpetual darkness and immense pressure, lies a landscape of epic proportions. Imagine a vast field of underwater dunes, not of sand, but of fine mud and silt, with individual waves stretching for a kilometer in length and cresting at heights of several hundred meters. For scale, that's as tall as a 50-story skyscraper. These aren't fleeting features. They are permanent geological formations, a testament to powerful forces that have been hidden for over 100 million years, buried about a kilometer beneath the modern sea floor. Geologists call these formations contourite drifts. Unlike the more familiar underwater avalanches that flow downslope, contourites are formed by the persistent, along-slope flow of deep ocean currents. These currents, driven by differences in water temperature and salinity, act like slow-moving rivers on the ocean floor, transporting and depositing vast quantities of fine-grained sediment over geological timescales. The discovery was made by geologists Dr. Débora Duarte and Dr. Uisdean Nicholson of Heriot-Watt University. By using seismic data, which creates a kind of X-ray of the Earth's subsurface, they noticed this striking layer of sediment waves. The sheer scale is hard to comprehend. Dr. Nicholson has compared their size to the overland dunes of the Namib Desert, one of the most extensive dune fields on Earth. The existence of these mud waves provides a direct, physical record of the ocean conditions at the time of the Atlantic's birth, telling a story of a turbulent and newly formed seaway. So how could something so massive be created on the ocean floor? The answer is a phenomenon of epic proportions, a massive, sub-oceanic waterfall of dense, salty water. This wasn't a waterfall like Niagara, but a powerful, gravity-driven flow of one body of water cascading through another, all happening in the dark depths of the ocean. The stage was set about 117 million years ago as the supercontinent Gondwana was breaking apart. As South America and Africa tore away from each other, a narrow, restricted seaway began to form, known as the Equatorial Atlantic Gateway. To the south of this gateway, in the brand-new constricted South Atlantic Basin, the climate was arid. This led to extreme evaporation, concentrating the salt in the seawater until it became a dense, hypersaline brine. To the north, in the central Atlantic, the waters were comparatively fresh and much less dense. For a while, a geological barrier, like a submerged mountain range or sill, kept these two distinct bodies of water from mixing. But as the tectonic plates continued to separate, this barrier was finally breached. When the gateway opened, physics took over. The much denser, saltier water from the south began to spill northward, sinking beneath the lighter, fresher water of the north. This created a powerful, deep ocean cascade that flowed along the seafloor, a submerged torrent of saline water. This was no gentle flow. This significant density contrast resulted in a strong, erosive current that picked up and transported vast quantities of sediment, mud, silt, and sand. As this sediment-laden current flowed, it deposited its load in the series of massive, wave-like structures we now see in the seismic data. It's a process akin to how wind sculpts sand dunes in a desert, but on a submerged and much grander scale. The 117-million-year-old mud waves are a frozen snapshot of this incredible event, a direct record of the moment the Atlantic Ocean truly began to connect. The discovery of these mud waves has sent ripples through the scientific community, compelling a major revision of the accepted timeline for the birth of the Atlantic Ocean. This geological birth certificate pushes back the date of this pivotal event by at least 4 million years. For decades, the prevailing scientific consensus was that the equatorial Atlantic Gateway opened sometime between 113 and 83 million years ago. This was based on evidence like the magnetic striping on the ocean floor. However, these mud waves provide direct, unambiguous sedimentary evidence of a fully established marine connection at a much earlier date. The waves could only have been formed by a powerful deep ocean current that existed once the gateway was open. By dating the sediments within these waves to 117 million years ago, scientists have established a new, firm start date for this critical phase of the Atlantic's formation. This revised timeline isn't just about changing a date on a chart. It has profound implications. It allows for more accurate reconstructions of past continental configurations and a better understanding of the forces that drove them apart. It provides a more precise timestamp for one of the final, most dramatic stages of the continental divorce between Africa and South America. In essence, the ancient mud waves are a geological clock that has been reset, allowing scientists to paint a more accurate picture of our planet's dynamic past. The birth of the Atlantic wasn't just a geological event. It was also a catalyst for significant and far-reaching changes in the global climate. This discovery forges a stronger link between the opening of the Gateway and a period of climatic upheaval during the mid-Cretaceous. The research suggests the Gateway's opening around 117 million years ago coincided with the onset of a period of global climate cooling. But the story is more complex. Before the Gateway was fully breached, the restricted basins forming between the continents are thought to have been sites of significant carbon burial. Like giant lakes, they accumulated vast amounts of organic matter, locking away carbon that would otherwise be in the atmosphere as carbon dioxide. The breaching of the Gateway and the underwater waterfall would have dramatically disrupted this. The powerful currents would have stirred up these carbon-rich sediments, potentially releasing large quantities of greenhouse gases. This could explain a period of global warming that's thought to have occurred between 117 and 110 million years ago, right after the seaway first opened. Then, as the Gateway continued to widen, it would have fundamentally altered global ocean circulation patterns. A fully connected Atlantic Ocean, with its unique north-south orientation, is crucial for transporting heat from the equator to the poles. The establishment of this system would have eventually led to a long-term cooling trend. Understanding these past climate events is critically important. By studying the feedback loops between plate tectonics, ocean circulation, and the carbon cycle in the geological past, scientists can improve the climate models we use to predict our future. The mud waves are a valuable natural laboratory for understanding our planet's complex climate system. This discovery is a compelling story of scientific detective work. It highlights the power of re-examining historical data with fresh eyes and modern technology. A key part of the research involved analyzing data from the deep-sea drilling project, which collected core samples from the ocean floor back in the 1970s. The scientists who first analyzed those cores provided crucial foundational data, but the full picture wasn't yet clear. Fast forward to today, and scientists like Duarte and Nicholson have access to modern seismic reflection data. This technique uses sound waves to create a detailed 3D image of the geology beneath the seafloor. When the team looked at this modern data, they saw the unmistakable signature of the giant mud waves. They then went back to the old DSDP cores, which had been physically drilled through these very layers. By integrating the two datasets, they could link the physical reality of the core samples their age and composition, with the vast picture from the seismic data. This is what allowed them to confidently map out the mud wave field and date its formation. It's a perfect example of how science builds on itself, with each generation of researchers using new tools to unlock secrets hidden in the work of their predecessors. To truly appreciate this discovery, let's travel back in time to the world of 117 million years ago. The mid-Cretaceous period was a greenhouse world, a time of high temperatures, high sea levels, and colossal creatures. The climate was significantly warmer, with little or no ice at the poles. Fossils of temperate rainforests have been found in what is now Antarctica. This warmth was driven by high concentrations of atmospheric carbon dioxide. On land, life was dominated by dinosaurs. In the skies, pterosaurs soared alongside the first true birds. Small mammals scurried in the undergrowth. A major revolution was happening in the plant world, with the rise of the first flowering plants. In the oceans, giant marine reptiles like plesiosaurs and mosasaurs were apex predators. The opening of the equatorial Atlantic Gateway was a pivotal event in this world. It created a new deep-water connection between oceans, fundamentally altering circulation patterns and creating new marine habitats. The formation of the mud waves is a direct record of this change, a geological scar left by the powerful currents that were unleashed as the world's oceans began to reconfigure. In the end, these gigantic mud waves, buried for 117 million years, tell an incredible story. They are the product of a colossal underwater waterfall that was unleashed when South America and Africa finally split apart. They have forced us to rewrite the timeline of the Atlantic Ocean's birth, pushing the date back by millions of years. And they provide a crucial link between the movement of continents, the circulation of oceans, and the dramatic shifts in our planet's climate. It is a powerful reminder that our planet still holds astonishing secrets in its deep, dark places. Secrets that, once uncovered, help us piece together the grand, dynamic story of Earth itself.